If we plot these parameters along with the characteristics curves of this BJT, then it will tell us that where this transistor is operating. This is the IC versus VPE axis at which the input characteristics curve were plotted. So here the input operating point of this transistor is 0.7 and 1.38. So we have gone to this axis, the VBE axis, to VBE, DC VBE 0.7, and then IC 1.38. We got this point at this graph. We have found these with this equation, right? It says that if we have a VBE, then for that VBE, IC can be found by this equation. To see how the change in VBE will move this point within this axis, the values of IC. To do so, let's just change this variable to a changeable. So that's why we put a total VBE and total IC instead of just DC values. And this is just the equation of a line having slope minus 1 by RB by beta plus RE by alpha, and this would be the y-intercept. The locus of this point for this line, that is the movement of this point possible with this equation, with this loop, can be found by just finding the extreme points and joining that extreme points. So to find the extreme point, let's just find the y-intercept and the x-intercept. To find the y-intercept, we can put VBE equals to 0, then this whole term will be vanished, and then IC would be equal to 1 by these resistances and the VBB, this point. Similar is the case for x-intercept. When we put the y value at this x-intercept equals to 0, then this whole denominator will be vanished by after multiplying with the 0, and then VBE would be equal to VBB. So these two extreme points we have found, and when we join these 2 points with a line, we can see that this equation is nothing but this line. And currently, because these points have been found hypothetically, that if IC is going to be 0, then what this equation can give the value of VBE, although it would be not possible. Similar is the case here, that if VBE is happen to be 0, then IC is maximum as far as this equation is saying. So but currently this transistor is operating at this point, and this point must be lying on this line. This is called the Q point, but at the input side. And if remember here that slope of this line is minus 1 by R in DC. What is R in DC? I actually named this RB by beta plus RE by alpha as R in DC. That is the input side loop, the slope of the input side loop for DC supply only. And this equation is nothing but the equation of this loop happened to be energized with a DC supply. That is why this equation would be called DC load line. If we plot the characteristics curve along with this load line, then we can see that this operating point is practical, not hypothetical. And this is hypothetical, because if we reduce VBE less than 0.5, we already know that this is a diode just at the base to emitter side, no IC would be flowing. But this equation says, but these are hypothetical points. So whatever at the input side, whatever is the Q point at the input side, it will be the intersecting point of your load line and the overall behavior, the characteristics curve of that transistor. Similar is the case for the output side. We have the output side, critical parameters at the output side are IC and VCE. So we have found VCE is equal to 4 volt and IC is the same. So if we plot this at the VCE and IC axis, which was the axis for the output characteristics curve, we will get this point. And this point actually we have computed by this loop equation, right? This VCE. If I also rearrange this equation for IC, I would be getting this. And similarly, if we want to see the change in VCE for a corresponding change in IC, or a change in IC correspond to a change in VC, we are bounded with this line because the transistor is now in this loop, bounded to work with this one. So to see how this line will allow the movement of this Q point, let's just change these constant value into the variable so that we can vary it. So here now we can see we have a slope minus 1 by RC plus RE by alpha into this. This is the slope and this is the y-intercept. So to find the locus of the points allowing by this loop that this Q point can move is to find the extreme points of this line, the y-intercept and the x-intercept. Again, if we put the y-intercept is equal to 0, we will be having VCE is equal to VCC. And if we put VCE is equal to 0, the y-intercept will be obtained as 1 by RC plus RE by alpha into VCC, like this one. And we named it as 1 by R out DC because this slope is within the output loop equation, so we named it as R out. And why it is DC? Because this whole equation is obtained with the DC supply only, so this line is called the DC load line. Remember, if you are given to find a DC load line, you have to find at least this output characteristics curved based DC load line. The input load line is not necessary. If you want, you can find. If it is asked to find, you have to find. Otherwise, if you are asked only to find the DC load line, it means only the DC load line at the output side, this one only. Now, going ahead, if we actually plot the characteristics curve of these transistors obtained earlier with this load line, we would be having these things. And we know that millions of curves are in between these curves. So this point can easily move along this line because the characteristics curve lying in between them. So a transistor has its operation within this. Yes, this can be a hypothetical point. As far as this equation is concerned, the transistor is not operating here because at this point the transistor currents would be here. So this is the Q point at the output side, this is the Q point at the input side, this is the load line at the input side, this is the load line at the output side. So far for a DC energized amplifier. To see
what happens if we insert an AC of 2 millivolt to this circuit in the presence of this DC supply. We will just see what will be happening with this Q point and how much volts we will be getting out of this circuit by applying only a 2 millivolt AC signal. But for quantitative gain calculations of this input AC to the output AC, we need AC analysis that will be done later. So let's just apply this AC signal and see what is going on with the Q point. This was the pure DC signal circuit we have analyzed already by Thevenizing it. So whatever we analyzed here is applicable here. And now if we want to apply an AC to this terminal, is similar to applying the AC signal to the Thevenized form of this circuit at this terminal. So whatever input is being injected, the input AC signal is being injected to this circuit is actually energizing this loop with the AC signal. So after applying this AC signal along with the DC signal, we would be having AC quantities as well besides the DC quantities, and the transistor and the amplifier will work for the total of this DC and AC quantities. These are the input DC load line and the output DC load line plotted along with the characteristics curve for your understanding. But now if we are going to apply this VI, what is going to happen?